All right, so our main purpose today, we are talking about electron transfer reactions. These are chemical reactions that involve the movement of electrons from one element to another as the reaction proceeds. Now, these kinds of reactions go by a number of different names. One of the names for them is electron transfer. Another one of the names for them is oxidation and reduction, oxidation-reduction reactions, named after the two processes that occur simultaneously in these reactions, oxidation and reduction. Now, the third common kind of term used for these is just a shortening of that last one, calling them redox reactions. Read for reduction, ox for oxidation. Now, the underlying principle behind these reactions is that we are starting to finally look at charge and the movement of charge in a chemical reaction. Thus far, we've only been concerned with the movement of atoms, the rearrangement of atoms to form new compounds, the rearrangement of atoms to create new substances. That's been our primary focus thus far. And we've gone from this standpoint of using balanced chemical equations to track that movement of atoms. But what we have to understand is that in a lot of cases, simply tracking the movement of atoms is not sufficient, because sometimes the atoms don't really move around a whole lot. It ends up being the electrons that do all of the heavy lifting. Now, there are two processes that take place here. One of them is something called oxidation. Oxidation is a process by which something loses electrons. We call that element that loses the electrons oxidized. In this process, we also have something called reduction. Reduction is the process by which something gains electrons. The element that gains electrons we call reduced. So I've got this interplay happening inside of a chemical reaction where one element is giving electrons to another element. And what's interesting about this is we know that this kind of thing happens pretty often. We've just used different names for it thus far. So take, for example, a single replacement reaction. A single replacement reaction, we had an element, usually a metal, and we know that metals on their own have no charge. Atoms in general don't have any charge. And we took that element, introduced it to some sort of ionic solution, and the end result is that that metal kicks out part of the solution and puts itself into solution and leaves behind a new metal on the other side. Well, let's think about that from a charge standpoint. I went from metallic elements with no charge to ionic compound with charge. To go from no charge to charge, electrons had to move in some kind of way. Look at it from the perspective of the element that got kicked out. It was charged. It was an ionic compound dissolved in water. By the end, it's been kicked out of the compound, and now it is a metal by itself. It went from having charge to having no charge. Somewhere along the line, electrons were transferred in this process. We didn't call it a redox reaction at the time. We called it single replacement. But the fundamental that led to that single replacement was the movement of electrons. We see these kinds of things happening in other kinds of reactions as well. Combination reactions. I take magnesium, metal, and oxygen gas, both of which are elements, both of which have no charge, Combine them together, I get the ionic compound magnesium oxide, where now the magnesium and the oxygen both have charges now. I went from no charge to charged. Somewhere along the line, electrons were moved. Decomposition reactions. I take a compound like water, where water we can kind of think of as having some charges with it, even though it's molecular. But we've got that hydrogen and hydroxide, positive and negative charges. If I electrify that water and it splits, I get hydrogen and oxygen, two elements, neither of which I have charge. I went from something that was charged to something that is uncharged. Electrons had to move in the process. So what we're really looking at here is most of the chemical reactions that we discussed in Module 4 are actually redox reactions. The only one that actually isn't a redox reaction is the one that we just spent the past 2 sessions on, double replacement reactions. Double replacement reactions are not redox reactions because all that we are seeing is the movement of ions from one area to another. The ions themselves don't change, their charges don't change, they just dissociate from each other and reassociate with other things. But aside from that, everything else we've talked about has kind of this movement of electrons in its fundamentals. Now, these terms of oxidation and reduction can very easily be confused with one another. So it becomes important for us to try to recognize different ways that we can remember these two processes and how they are different from each other. So there are 2 common mnemonic devices that are used for this purpose. Your book focuses on the one here on the right, oil rig. Oil rig stands in OIL-RIG. OIL, oxidation, is loss. Rig, RIG, reduction is gain. Now, in both sets of cases, we're talking about electrons, so we can make that a little bit more clear. Oxidation is the loss of electrons. Reduction is the gain of electrons. So that's oil rig. That's what's used in your textbook. All references that you're going to see to these mnemonics in your book are going to be oil rig based references. I bring up Leoger on the left there. That's actually the one I learned when I was in high school. And one of the reasons I learned it is because it is corny as all get out. And you'll be even cornier in about 15 seconds. But sometimes it's the corniest stuff that sticks with you the longest. And so Leoger breaks down into 2 parts again. Leo, L-E-O, loss of electrons is oxidation. G-E-R, ger, gain of electrons is reduction. Leo, ger. Leo the lion goes, ger! Which one you use doesn't matter to me. But chances are pretty good you're going to want to use one of them to help you keep these terms straight, because it's very easy to get them flipped around, and it's even easier to get them flipped around when you start to incorporate their actual reactions into your study and not just looking at oxidation states and how they're changing. So let's take a look at some examples of reactions that follow this line. So on the left here, we have an example of a synthesis reaction, magnesium being oxidized by oxygen in the air. That process involves, we've got magnesium reacting with oxygen to make magnesium oxide. And you can see in this setup exactly what I was trying to get across a couple of minutes ago. On the left-hand side, on the reactant side, you've got elements, uncharged atoms. On the right-hand side, you've got an ionic compound. That ionic compound is made up of ions. The ions themselves are charged, even though the overall compound is neutral. In the second panel, we have an example of another synthesis reaction that also can work as a combustion reaction of sorts. I've got calcium reacting with oxygen to make calcium oxide. And again, the same kind of thing's apparent here. Elements on the left-hand side, no charge. Ions on the right-hand side, charged. Here's an example of a single replacement reaction. In this single replacement reaction, we can see, first of all, we can see one of the really useful applications for net ionic equations. Notice here, the solution that this silver is in as a reactant is probably silver nitrate. Why don't we see the nitrates here in this chemical reaction? Well, they're spectator ions. The nitrates aren't actually participating in the reaction. They're just kind of floating around in the solution. And so we omit them for greater clarity here. And now that we have that clarity, it becomes a lot easier to see how the electrons are moving in this chemical reaction. Because I can see that, oh, okay, the copper here is changing. It went from no charge to positive 2 charge. Well, to become more positive, you have to get less negative, which means you had to lose electrons to get there. Loss of electrons is oxidation, Leo. So I could say that the copper is oxidized in this process. And similarly speaking, I could look at the silver ion and see that we are going from silver ion to silver metal. I'm going from a positive state to a non-charged state. Well, to get less positive, I have to get more negative. More negative would mean I had to add electrons. So the silver ions are gaining electrons. The gain of electrons is reduction, GER. And so by comparing the charges before and after, I can get a sense of what's being oxidized and what's being reduced. So in a single replacement reaction like this, it's usually pretty easy to see what's being oxidized and what's being reduced because the charges are changing so drastically and so clearly and obviously when we break it down into a net ionic kind of form. The question becomes, and where this gets tricky for us, is what if I don't have that kind of simple form to show what my charges are? How do I determine how the electrons are moving in a chemical reaction? How do I determine if electrons are moving in a chemical reaction? To answer those questions, we need to talk about something called an oxidation number. Now, an oxidation number is kind of like the personal charge on an element in a given substance. So we can evaluate the individual charges on individual atoms in compounds through oxidation numbers. And in order to identify a redox reaction, we look for changes in these oxidation numbers as we go from the reactant side over to the product side. Now, going about assigning these oxidation numbers can be a little bit of a process. But luckily, we have a few guidelines that can kind of help point us in the right direction. The first guideline, and this guideline supersedes all other guidelines. The first guideline is this: the sum of all of the oxidation numbers in a given substance has to equal the charge on that substance. So if the substance is uncharged, neutral, all of the oxidation numbers have to equal 0. If the substance is an ion, all of the oxidation numbers have to equal up to the charge of that ion. And so what this sets up for us is some really interesting kinds of implications. Because first of all, one thing that we can do is we can look at elements and say, okay, I've got sulfur here. Well, it has no charge, so its number must be 0. I've got chlorine here. Chlorine has no charge, so the oxidation state must be 0. I've got manganese ion here. Manganese is the only element in this ion, so its charge must also be its oxidation number, +2. If I get into more complicated substances, then I just need to extend this rule a little bit further. So what if I have a compound like dichlorine monoxide? What if I have an ion like the permanganate ion? Well, in those cases, I know that the sum of my oxidation numbers is going to give me the overall charge. So in the case of the dichlorine oxide, I've got chlorine and oxygen, and together they're going to make a total charge of 0 because chlorine dioxide is a neutral molecule. Now I can simplify this because chlorine and chlorine are going to have the same oxidation number because they're the same element. I could simplify this to be 2 chlorine and oxygen have to equal 0. And that would make the algebra a little bit easier to do. For the permanganate ion, same kind of thing. The charge on the manganese plus the charge on each of those 4 oxygens has to equal the total charge of the ion, which is -1. Since each of those oxygens would have an identical charge, I could simplify that as manganese and 4 times the charge on the oxygen would give me a -1 overall. So these are the things that we can do using this first rule to at least start to point us in the correct direction. Now, if I have an ion or an element that is easy, only one type of element in it, then I know what to do. I just take whatever the charge is, and that's the oxidation state also. If I have compounds or polyatomic ions, I've got to do a little bit more. And here's where the second guideline would start to come in. Because if I'm looking at the permanganate ion, I'm not exactly sure how to tackle this algebra problem. Right now, it's got two variables. You know as well as I do, you can't solve two variables with one equation. You need some other kind of piece of information. So here's where that some other kind of piece of information comes in. Because some elements are more likely to draw electrons to themselves than others, certain elements have well-known, well-defined oxidation states. So we haven't talked about electronegativity yet. It's something that we'll talk about more when we talk about chemical bonding. But the idea of electronegativity is basically how well does an element draw electrons to itself when it's bonded to other elements. The better it is at drawing electrons to itself, the more likely it is to have a negative charge. Fluorine and oxygen are the two most electronegative elements on the periodic table. They're the most likely to carry their most common charges. Most common charge for fluorine is -1. Most common charge for oxygen is -2. We know that based upon their position on the periodic table. And so when we look at the oxidation states of fluorine and oxygen, what we see is that coming through. We see fluorine being -1 when it's in a compound. We see oxygen being -2 when it's in a compound. And the only real exceptions to those rules are when those elements are in compounds of their own. So if fluorine is in its elemental diatomic state, it's not going to have a charge because it doesn't have a charge overall. Oxygen, same way. The only other exception on the oxygen is we know that peroxides exist. Peroxides are two oxygen atoms that share a -2 charge. And so if I look at each atom of oxygen individually, I would say that each oxygen only had a -1 charge. -1 for the first oxygen plus -1 for the second oxygen gives a -2 overall. This other guideline here has nothing to do with electronegativity, just has to do with the fact that hydrogen really doesn't have many options. Hydrogen has one electron. Because of that, it can only really have 3 oxidation states because of the size of that first energy level. When it's an element by itself, its state is 0, just like every other element. When hydrogen is acting like a metal, which is most of the time, and reacting with non-metal substances, which is most of the time, its oxidation state is going to be +1. On those rarer occasions when hydrogen is acting like a halogen and reacting with metallic substances, it's going to carry on the halogen -1 charge. But again, that's on the rarer side. Most of the time, hydrogen is +1 when it's bonded to other stuff, or 0 when it's by itself. And so with those kinds of things in mind, suddenly our algebra problems here become a lot easier to solve. Because in both of these cases, I was dealing with oxygen. So if all of a sudden I'm looking at manganese and 4 -2s make -1. 4 times -2 is -8. Manganese minus 8 equals -1. Well, if I add 8 to each side, I get manganese at a +7. Now I know its state. Manganese is +7 in that particular ion. The oxygen was -2. For the dichlorine monoxide, well, I had 2 chlorine plus oxygen equaling 0. Now that I know that oxygen is -2, I need to add 2 to both sides. 2 chlorines equal +2, which means that each chlorine must be +1. So now I know what to do with it. Now I can kind of look at it and go, okay, this makes sense. This is the next thing. All right, questions with oxidation numbers before we do some examples and look at some reactions. All right, let's do this part together. So if I'm looking at oxidation states, let's say that I wanted to find the oxidation numbers for all of the elements here in potassium dichromate. Potassium dichromate, K2Cr2O7. Here's a trick that wasn't on the guideline sheet, but is still really useful. When I'm dealing with ionic compounds, and I know this is an ionic compound because I've got metallic and non-metallic stuff together. When I'm dealing with that, I want to split that compound into its 2 ions, into the positive ions and the negative ions. So when I split this apart, I'm going to have potassium ion and dichromate ion. The important thing to remember about this splitting process is we have to note that subscripts are there for balancing purposes and balancing purposes only. So that 2 on the potassium, that doesn't register as anything other than just a balancer. If we were doing an ionic equation, we would pull that 2 to the outside there to let you know that there were 2 potassium ions there. K2 doesn't exist as an ion. So from this, now I look at my ions and I go, okay, I know what potassium is. Potassium is a monatomic ion. It has a +1 charge. The only possible oxidation state it could take is +1. And so that one we've got solved right there. For the dichromate, now we need to set up one of those algebra problems. For dichromate, Cr2O7 -2, I've got 2 chromium and 7 oxygen, and they have to add together to give me the charge of -2. Going back to the previous slide, I know that oxygen is -2 in most circumstances, in most compounds. So if I do the math, 2 chromium minus 14, 7 times 2 is -14, is equal to -2. To get the chromium by itself, I need to add 14 to both sides. That's going to give me 2 chromium is equal to positive 12. To get rid of the 2, I need to divide each side by 2, which means that the chromium is going to be positive 6. So if I have an ionic compound, that's exactly what I need to do. Take that compound, split it up into its ions, and evaluate each ion individually. Usually speaking, since the cation is usually a metal, we'll be able to determine the oxidation state of that metal just by knowing its charge. Really, the only cation that doesn't behave that way is the ammonium ion, and that's because that one's a polyatomic ion as well. Every other ion that we've dealt with that is positively charged is a metal from the periodic table, and we can derive its charge from how many of the other ions are there. For the polyatomic ion, we just break it down. Usually polyatomic ions have oxygen in them or hydrogen in them or both. And so since oxygen and hydrogen have very well-known values, we just break it apart and solve for what is left. All right, questions here with this example? Okay, here's where it can get a little bit confusing for us. It's one thing to be able to assign oxidation numbers. What can be a little bit difficult is starting to put some descriptors on the substances that are actually reacting. So oxidation numbers help us to identify elements that are being oxidized or reduced. The terms oxidizing agent and reducing agent describe compounds, substances that are going to be part of the process itself. And where it gets confusing is we identify these agents based on their action, not on the result. So what do I mean by that? So an oxidizing agent works by basically ripping electrons away from the other compound. So in the process of the oxidation reduction reaction, the oxidizing agent takes electrons away from something else. So the oxidizing agent doesn't get oxidized, it oxidizes something else. It forces that action on another substance, on another element. Reducing agents, on the other hand, are substances that force reduction, that will cause other substances to take electrons. Now, the important thing to remember here, these two processes do not occur in isolation. They occur in tandem. You can't have one without the other. So the important thing to remember is that this isn't some sort of like abusive relationship where the oxidizing agent shows up, knocks on the door, and then steals all of the other substances' electrons. This is a mutual relationship. The oxidizing agent shows up, the reducing agent opens the door, says, take what you need out of the fridge, and they part ways with different numbers of electrons than they started with. The two processes happen at the same time. And so in the process of forcing oxidation, that substance will grab those electrons and reduce one of the elements inside of that oxidizing agent. In the process of giving those electrons away, those electrons had to come from somewhere. They came from one of the elements inside of that reducing agent. So one of the elements in that reducing agent gets oxidized in the process. The two are working in tandem. They're working together. You literally cannot have one without the other. So let's take a look at an example of this. Here we have a very common process used in the purification of iron for steel. You've got iron ore in the form of iron 2 oxide reacting with graphite to make iron metal and carbon monoxide. If we look at the processes themselves, what we will see is that the iron in the iron oxide converts from being positively charged in the oxide to having no charge as an element. We can see in the process from going from a positive 2 oxidation state to a 0 oxidation state, it has gained electrons along the way. So we would say definitively that the iron is reduced in this process. Makes sense. The iron has lost some of that charge. It's gained electrons. Consequently, we could look at the carbon and see a similar kind of fate, only in reverse. It's gone from a 0 state to a positive 2 state. Along the way, it has lost 2 electrons. And so we would say, rightly so, that the carbon has been oxidized. So those are the processes of oxidation and reduction. Now, if we're talking about the reactants themselves, this is where we need to make those distinctions. We can talk about the iron oxide forcing the oxidation of this carbon. And so we would call it the oxidizing agent because of that. The iron oxide forced the carbon to get rid of its electrons. The carbon, on the other hand, forced the iron oxide to take those electrons. So we can call carbon the reducing agent. Most important thing to remember here as we're evaluating these, oxidizing agent and reducing agent are always referring to substances, not just elements. And they're always on the reactant side of the equation. Because we're always talking about what they are doing to make the products. So, kind of an easy way to remember this, elements get oxidized and reduced. Substances, reactants, are oxidizing agents and reducing agents. Sometimes they're one and the same. In the case of the carbon, carbon was oxidized. It was also the reducing agent because it as an element was the reactant. But if my element is part of a compound, that compound is either the oxidizing agent or the reducing agent. All right, let's do a little bit of practice with oxidation numbers, and then we'll call it a day for today. On Friday, we'll do a couple more examples, just walking through some oxidation, reduction, redox stuff, just to kind of see how much of this stuff stuck. And then we'll get into numbers and calculations for the end of Module 5 on Friday as well. So starting with letter A here. What is the oxidation state of sulfur in S8? All right, say that louder, Isaac. Okay, this one can be a little bit tricky. A lot of our non-metallic elements form these molecular compounds in their elemental states. Doesn't matter how many atoms are there. If they're all the same and the whole thing has no charge, then the oxidation number is 0 in those cases. So it doesn't matter if we look at S8 or P4 or Cl2. All of them are going to have 0 oxidation states because they have no charges. For B, we're looking at sulfur dioxide. In the case of sulfur dioxide, we need to look at that first guideline again. Sulfur and the 2 oxygens have to equal a total charge of 0. Since each oxygen is -2, S is going to be added to -4 to get to 0. So the sulfur must be +4 in charge. For letter C, sodium sulfide, this one's pretty easy. Why is it easy? I should recognize this as an ionic compound. And if it's an ionic compound, I want to split it into its ions. And in this case, the oxidation state is the charge because there is nothing else on that substance. There's no oxygens, there's no chlorines, there's no anything other than just the sulfur itself. So the sulfur's oxidation state there is -2. For letter D, we have a different compound, a different ionic compound, calcium sulfate. We still want to treat it very similarly. Split apart the calcium ion from the sulfate ion. And now that we have the sulfate ion, now we can do a similar kind of algebra. Sulfur and 4 oxygens make an overall charge of -2, because that's the charge on the sulfate ion. Since each oxygen is -2, sulfur and 4 times -2 is -8. Make -2, add 8 to both sides. The sulfur is +6. So with some practice, you should be able to get pretty good at assigning oxidation numbers because the guidelines that you use are relatively straightforward. Charge matches, sum of oxidation numbers matches the charge. Elements are always 0. Ions match up. If they're polyatomic, I've got to do algebra. If I've got a molecular compound, I've got to do algebra. But all the algebra is really pretty straightforward, algebra 1 from high school kind of stuff. So hopefully you won't get into too much trouble with the material this evening and tomorrow night. On your way out, make sure to hit the stoplight question. And if you do have any questions between now and Thursday night related to the homework assignment, please feel free to reach out to me in any way that you know how. Have a great afternoon. Go ahead and get one.